pick up where we left off last time. Not starting a new document. We talked about trees, which are graphs that are connected. You get from any vertex to any other vertex, but they don't have any cycles. So there's nowhere that you can kind of go around in a loop and end up back where you started. These show up a lot, and they have a lot of special properties. So here is one. We noticed that it seemed like there was always exactly one more vertex than there were edges. So like if we had 10 vertices, we had 9 edges, and so on. And we tried a bunch of random examples, including one that you all kind of randomly chose, so it wasn't just me sneakily picking good examples. Seems like this is always true. So we're going to prove it. And I guess the way we're going to prove it is slightly sneaky because, you know, if you just look at what the theorem says, if you tried to write down the theorem in formal propositional logic, it would say for all graphs, you know, if the graph has more than at least one vertex and it's a tree, then number of edges equals number of vertices minus 1. And but we're going to kind of transform it a little bit into a statement that says, well, for all natural numbers, if that number is the size of a graph, then you know that graph will have these properties. So it ends up being the same thing because every graph has some number of vertices. So, but kind of instead of directly proving something for all graphs, we're going to prove something for all graph sizes, and then we can use normal induction on natural numbers. So we can say, we'll look at size k, and then size k plus 1, stuff like that. Okay. And this is a pretty common technique, especially when proving stuff about graphs, because often we can kind of, this idea of like, if we can prove it for smaller graphs, then we can prove it for bigger graphs, then we can build up to all graphs. Okay. So, we already did the base case. Our induction step, right, we're going to suppose that every finite graph, which is a tree, that has k vertices, I should really say, you know, let k greater than 1. Just say k is an arbitrary something greater than 1. Okay. So our induction hypothesis is every graph with k vertices, every tree with k vertices has you know, k minus 1 edges. And then we have to show that it's still true for every graph with k plus 1 vertices. Okay, so suppose, I'll just say let G be an arbitrary graph with k vertices. Okay, and suppose, right, because the thing I'm trying to prove says if the graph, you know, has is a tree, then so I'm going to suppose G is a tree. That is, G is connected, and to introduce a fancy math word, acyclic, that means, i.e., has no cycles. On the one hand, I don't want to introduce too many terms, but it's going to be nice to just be able to say acyclic rather than having to always say has no cycles. Okay. Okay, I already did something wrong. Right? Well, we want to show that this is true for every graph with k plus 1 vertices. So I should have said k plus 1 vertices here. We already are assuming that graphs with k vertices have this property, so I don't need to say anything about graphs with k vertices. And this is yeah, I'm sorry that I messed it up, but maybe it's a good opportunity to mention. Right, induction always goes this way, where you say we assume it's true for k, and then we have to show it's true for k plus 1. So we would start by saying, suppose I have something of size k plus 1, I get to use the fact that, so if I can somehow come up with a thing that's smaller, I could use my induction hypothesis. For some reason with graphs in particular, it seems like I've seen students often get confused and try to do it the opposite way, where they say, okay, suppose I have something of size k where it works. Now I'm going to show how to make it bigger into something where it still works. But that is not quite right, because again, we would have to be sure that every possible graph of size k plus 1 you could get by starting with something of size k and making it bigger. And that's not necessarily obvious. So we should start with an arbitrary thing of size k plus 1, and then we know that it's going to work for anything. Okay, so our goal is, somehow we have to come up with some related graph that only has k vertices, and we can then use our induction hypothesis, and then somehow put a vertex back. So if we can find a vertex to delete somehow, then we can use our induction hypothesis on what's left, and then put the vertex back and conclude something about the original graph. That's our strategy. So in particular, in this case, what I want to do, if I had a graph like this, I definitely don't want to delete this vertex. Right? Because if I delete that one, I'm just going to be left with 3 vertices by themselves. And I would not be able to use my induction hypothesis then. Because it would have size k, but it wouldn't be a tree anymore. And my induction hypothesis only says something about graphs that are trees. So in order to keep it a tree, what I have to do is I have to find a vertex of degree 1, also known as a leaf. If I can find one of those, then I can delete it. If I delete that vertex and that one edge, the thing I'll be left with will still be a tree, because I didn't make it disconnected by deleting. So we want to find a leaf to delete. Okay, and so I claim G has at least one leaf. That's not necessarily, if we draw a bunch of trees, it's like, okay, yeah, it looks like they always have leaves, but how do we know that for sure? How do we know we can always find a leaf? It turns out, in fact, every tree has to have at least 2 leaves, but we don't need that fact. 1 is enough. So why? And it's not enough just to draw a bunch of trees and be like, look, here's a bunch of trees. Look, they all have leaves, right? That's not a proof. We need to use what we know about trees to argue why we can always find a leaf. So here's how I'm going to prove this. I'm basically going to give a procedure for finding a leaf. So to find a leaf, so 1, pick an arbitrary starting vertex. Right, and my graph can't be empty because it's got k plus 1 vertices, so it definitely has at least 1 or 2 vertices or something. And then step 2 is take a walk. What I mean is, just start following edges. If there's an edge next to the vertex I start at, I'm going to follow it. And then I'm going to follow another edge, I'm going to follow another edge. Okay? So, i.e., keep following a path of edges. Right? But never reuse an edge. Okay, so if we somehow come to an edge that we've already gone on before, don't go on it again. So claim you will eventually get stuck at a leaf. Or I should have defined find here what leaf means. Leaf equals vertex of degree 1. And that is a generic graph term. I mean, it sounds especially, it makes a special sense when we're talking about trees. Because like, what's at the very tip, the end of the tree? Leaves, right? But the term leaf actually applies to any graph. If you have a vertex of degree 1, you can call it a leaf. At a leaf. But because if I come to a leaf, I'm definitely stuck because I just came along an edge to get there, and the only way to get away from it would be to go back along the edge I just came on, and I can't do that, right? So, if we get to a leaf, we will definitely get stuck. The question is, why will we get to a leaf? So, we can't get stuck at any vertex with degree greater than 1. Because, you know, if I come into it along an edge, there will always be at least one other edge going, you know, that can go out because it's got degree 2 or greater. You know, it might look like this. So if I come in this way, then I could, you know, go out this way. Now, the other thing we might worry about is that I might, I could get stuck at a vertex if I like come back to a vertex that I've already been at and I've already used the edges that are there, right? Then I can't use them again. But that'll never happen. Why can it never happen that I'll come back to a vertex that I've already been at before?
Here, no cycles.
Right, because this graph, we're assuming it's a tree, has no cycles. So I can never get back to somewhere I've been before. And never come back to a vertex we visited before since there are no cycles. And the final thing is we have to use here the fact that the graph is finite. Because if the graph was infinite, then actually I could just walk forever, never repeating the same vertex and never finding a leaf, right? But we know it's finite, and so this can't go on forever. I can't keep visiting new vertices forever because there's only so many vertices. Since G is finite, we will eventually run out. Okay, makes sense? So not only have I proved that there has to be a leaf, I've actually given a specific way to find one. Start at a vertex and just start walking. Eventually, you'll get stuck, and when you're stuck, it's because you found a leaf. It's not necessarily the most efficient way to find a leaf possible, but it works. And if you didn't already know anything about the graph, you know, like if someone like blindfolded you and put you in a helicopter for some sadistic reason, I don't know, and they dropped you in the middle of a hedge maze, and they're like, this maze is definitely a tree, you know, and there's exits at the leaves, right? Then you're like, cool, no problem. I'll just start walking, and you'll eventually find it. As long as you never just turn around and go back the way you came, you'll find a way out. That'd be a pretty dumb hedge maze, but you know. Okay, so call a leaf vertex L for leaf. If we remove L and the incident edge, G looks something like this. Right, so maybe this is L here. And so we're going to remove that vertex and edge. Then what are we left with? We are left with a graph, I'll call it G prime, that has k vertices, because we just removed one. And it's still a tree. Why is it still a tree? Well, because I was careful to remove a leaf, I couldn't possibly have made it disconnected. Because, any two vertices, if there was a path between them before, that path couldn't have possibly used this edge, because the only thing this edge would be good for is finding a path to that leaf that we deleted. So I left all the paths intact, so it's still connected. And if there weren't any cycles before, I certainly can't make any new cycles by deleting an edge. So it is still connected since we removed a leaf, and still acyclic since removing an edge can't create cycles. Okay? So, our induction hypothesis says, here it is. This is our induction hypothesis here. If we have a finite tree with k vertices, then it has k minus 1 edges. So we conclude, right, this G prime is indeed a finite tree with k vertices. So by our induction hypothesis, G prime has k minus 1 edges. Okay, but what was G? Our original graph G was just G prime plus an extra vertex and edge. So obviously, G has k edges, and then G has k edges, since, let's say, we deleted one edge from G to get G prime. Okay. Any questions? So this is sort of a paradigmatic proof about graphs. A lot of proofs about graphs use induction on the number of vertices, and we'll work this way by saying, well, let's find some things to delete. Show that the things with the right properties exist, and we can delete them, and then we can use our induction hypothesis and then put the things back. And even some graph algorithms work that way. And if you take algorithms with me in the fall, then we'll definitely talk about some. I'm thinking in particular of an algorithm called Topological Sort that kind of works this way by at each step it kind of picks an appropriate vertex that it puts in part of the output, and then it deletes it, and then it kind of keeps going to the rest of the graph. And the reason that algorithm works, you could prove it by induction using a similar approach. The interesting part when you're writing algorithms is for example, the way we found a leaf is not the most efficient way to find a leaf. If you do it that way with the algorithm is unnecessarily slow. So part of the interesting thing there is, okay, how do we keep track of stuff so we can do it more efficiently? But I won't get into that now. Get into that in the fall. Cool. So my plan rest of today and Friday, we're just going to explore one or two kind of other interesting, kind of classically interesting graph theory problems and how they ended up getting solved. And actually, we actually go to the website. So I don't know if anyone ever wondered. Maybe you never thought about this. But what is this picture which is in the background of the street map website? So I will tell you what it is. It is actually an old drawing of the city of Königsberg, which I guess now is like, it's modern day, what is it called? Starts with a P. St. Petersburg, Russia. But, Königsberg had, there are some rivers that go through it. Let's see if we can draw this. Island here. So this is all water. So this is the Prego River. And this is an island. So the city kind of had, I guess it's like two rivers that come together here, and then there's an island in them. And there were some bridges. And actually, this is sort of, those are the colors we use for bridges. Orange. If you go to the city now, it's not the same bridges that are there now. This is where there were bridges before. So there was a bridge here. There was a bridge here. And here. Okay, this is a big island with a lot of bridges. There's a bridge here. And then also a bridge over this branch of the river. A bridge over this branch of the river. Okay. And yeah, and if you, I don't know, if you go back to that picture on the website, you can kind of, you can see the river and you can see some of the bridges going up it. So the people in the town kind of had a challenge, which was to start somewhere in the town and walk over every bridge, in some order, without ever going over the same bridge twice. So I'll give you 1 minute to see if someone can come up with a solution how to walk across every bridge without going over the same bridge twice.
I was going to make a joke answer, so I was going to say she wants to do the joke, so I'm just not going to say it.
Okay, fine. Anyone? So, no one in the town could figure it out either. But they really weren't sure whether, was there some clever way to do it and they just couldn't figure it out, or was it really impossible? I think a lot of people were probably kind of convinced that it wasn't possible, but they didn't know for sure. So don't feel bad. There's actually no way to do it. And you could if you dynamite a bridge or something, maybe there's a way to do it if you get rid of a bridge or add another bridge. What was that? If you swim, yeah. If you can swim, then you can do it also. But yeah, I'm assuming that you're not going to swim. Is that part of your joke answer here?
I was going to say if you go far enough in one direction,
Oh.
come sort of back around.
Oh, I see. If you go this way far enough, maybe you can go around the headwaters of the. Yeah. true too. I think the idea was that you you start in one place in the morning and then you do this walking tour of the city and you end at like a pub and go for a drink with your friends. So going like way out of your way was not an option. You would miss the pub. So there was a guy named Euler. You may have heard of him. He's lots and lots of math things named for him because he was like incredibly prolific and wrote like hundreds of papers. You know, if you've used the number E, that's named for him. There's like Euler's formula, there's Euler's theorem, there's like all this thing. So Leonhard Euler. In 1736, this is when he heard about this problem, and he's like, all right, I'm going to solve this problem. So in order to solve this problem, he invented graph theory, basically. No one had ever really thought about graphs in kind of an abstract sense in terms of things being connected, with edges, whatever. But he realized that, like, the fact of the physical nature of the city and, like, where bridges are and stuff, that doesn't matter. And so he was able to kind of say, really the important thing is there's basically three places you could be. Like, you could be on, down here, or you could be over here, or you could be up here, and then there's different ways they're connected. And then we're kind of looking for a way to go through the graph. So basically, invented graph theory to solve the problem. Okay, so we can abstract from this a little bit. We abstracted from this and said, well, really, essentially, we have three vertices, right? There's a vertex, this is like 1, this is 2, and this is 3. And then there's some edges between them, right? So 1 and, oh no, wait, there's 4 vertices, sorry. The island is a vertex also. Maybe that didn't seem quite right. Hold on, 4. Yes, okay. So there's 2 edges from 1 to 4. There's 2 edges between 4 and 2. There's an edge from 4 to 3. There's an edge from 1 to 3, and an edge from 2 to 3. Okay? So we kind of abstracted the town and the bridges into this graph. And so now the question becomes, is there a path in this graph, a simple path that never repeats an edge, that visits every edge? Right? Can you make a path through the graph that visits every edge? So, question, is there a simple path? So simple means no edge repeats in this graph that includes every edge. Right, and then he started thinking more generally about, okay, what features of a graph would make this possible or impossible? So, okay, we can just say definition, an Euler circuit, or an Euler path. Right, so here's another thing that's named for Euler. These kinds of paths are named Euler paths. Euler path is a simple path containing every edge of a graph. And we can also say an Euler circuit is an Euler path that is a cycle. So one thing to emphasize here is that maybe mean different things sometimes. In this case, we actually don't, we are okay if the path repeats vertices, right? Because so surely you're going to have to, you know, like if I start here and go over here and then come back up here, I'm going to, you know, be in vertex 1 twice. That's okay. The thing I can't do is repeat an edge. So in this case, we are okay with repeating vertices, but we're not okay with repeating edges. So note, repeating vertices is okay, but not edges. All right, let's just brainstorm some examples. So, can someone give me an example, or a few examples of graphs that do have an Euler path? We don't know about this one yet, but let's just see if we can think of some simple graphs that do have an Euler path. Okay.
2 dots with 2 lines.
Okay, 2 dots with 2 edges. Yep, and in fact that has an Euler circuit, because we can like start there, you know, we can come back to where we started and visit both edges on the way. Okay. So it says, actually let's do it, let's do this. Okay. Another example.
Like a triangle, like, you know, 3 dots.
Yep, agreed. So that has both, right? Okay. Catherine?
1 vertex and 1 edge.
Vertex, 1 edge. You mean like a self loop? Yeah. Okay. Yeah, so that also has both, right? How about, we'll just come up with some examples of either ones that have an Euler path but not an Euler circuit. Also, so we can come up with some simple examples of graphs that don't have either one.
What's the definition of a circuit then?
An Euler circuit is one where we can start at a vertex, visit every edge, and come back to where we started. An Euler path, more generally, we might end up somewhere, we have to visit every edge, but we might end up somewhere different than where we started. Yeah.
2 vertices and an edge.
Yeah, so like this. So this one has an Euler path. We can visit every edge, just the one, but we can't come back to where we started. So. Okay, what else?
I think that, so it would be 4 vertices, so basically a triangle with a vertex in the middle.
And okay, how do you want to connect them?
Like make a triangle and then connect all of them to the middle.
Oh, okay.
I think that has a 9 vertex.
You sure? How do we know? Yeah, I mean, I think you're right actually, but maybe not clear. How about, let's do something even simpler. How about like, this? Maybe this one we can convince ourselves whether it does or not. So what do you think? Does that one have an Euler path or circuit? See some shaking heads. Adam?
Yeah, because you end up having to choose one of 2 paths, and wherever you start, you can't repeat a vertices, or vertex.
Yeah, if we start here, I mean, we can, you know, really one choice where to go. We could go here, and then whichever way we choose, we think it's stuck. And we can't go the other way. Or if we start in the middle, well, fine, we can just go out one of the versus all where we need to stop. So, yeah, so this actually has neither. Anyone, we could do some more examples, I guess, but anyone have any guesses or ideas about kind of things that are relevant about the graphs? Like what are some things about the graphs that make it impossible or not possible? Or yeah, okay.
Feels like there's a vague connection in terms of if all of the degrees are on numbers greater than 1. Is that the same for those two and also the previous example?
Okay, interesting. So you're saying these two that didn't have any Euler Crowther circuit, all the vertices had an odd degree.
And maybe you could apply that to the line with 2 dots, but then it's also odd and it just doesn't have a circuit.
Right. Okay. Yeah, yeah. Yes, maybe there's something about odd degrees or degrees greater than 1. Yeah.
Would you scroll up so I can see it?
Oh, sure.
But, I was kind of saying, it seems like we can kind of break it down into like maybe smaller shapes, like kind of you did with that triangle there. Like maybe we can break it down smaller, like see how we've decided that this one circuit, you know, is a circuit. So, but here we have 2 up there, but we know 2 in a row. Why wouldn't that just be like, just 2 circuits together? So it seems like maybe we could take this apart by looking at like the shapes individually.
Okay. Yeah, I like that. Good idea. So you're saying maybe there's a way that we could look at this graph here and kind of break it down into smaller graphs somehow, and then kind of use what we learn and put together what we learn somehow to figure out the integral graph. Yeah, that's a great idea. It's maybe not clear exactly how we would do that, but it is a good idea. Well, one thing I will say, right, so for example, if I have a graph, you know, some graph here, and then some other graph H over here, but like, they just share a single vertex, right? There's like one vertex where they're connected and everything else they don't connect. If G and H both have an Euler circuit, then we can kind of like go along the circuit for G, and then when we get to that shared point, we kind of take a detour and go all the way around H, and then we continue along the circuit for G. So that would be one way we could put, you know, break it down into smaller graphs. Okay, so I want to explore this idea. So we will come back to Grace's idea later, in fact. I want to explore this idea about the degrees of vertices. There was kind of a reason that we talked about degrees earlier. I will make an observation. Right. So let's say that I've got I'm somewhere in the middle of a graph, right? And I've got vertices that look like this. And as I'm coming along, I'm doing a path, right? As I'm coming along here, I come into this vertex, and then I go out of this vertex. Oops. Right, well, actually, I don't even need to draw all of this, really. It's just like, you know, this vertex has some edges connected to it. And when I visit this vertex, I'm going to come in along one edge, and then go out along another edge. And I can't reuse either of those edges, right? So I've used up 2 edges connected to that vertex. So say every time we visit a vertex, we use up 2 edges that we can never use again. Okay, and obviously every time we do that, it's okay to visit a vertex multiple times. So maybe I would later come in and, you know, after I go around, you know, and then I come in along this edge, and then I leave along this edge. I've used up 2 edges again, right? So like the number of available edges at that vertex always goes down by 2 every time I visit that vertex. You know, and eventually, if the degree of that vertex was odd, then eventually, after I do this enough times, there's only going to be one edge left, and I'm going to get stuck at that vertex. Because if I come to it at all, there'll be one edge left, and then I will have no edges remaining by which I can leave. Right? So if the degree is odd, eventually, right? And like I have to visit every edge, so I'm gonna if I'm gonna make this work at all, I've got to like keep going through the vertex to use up all the edges. But if it's odd, eventually there will be only one edge left, and we will get stuck there. So I'll ask a slightly abstract question, hopefully makes sense. But if we're trying to find an Euler path or an Euler circuit, when is it okay to get stuck? Like, is it ever okay to get stuck?
When you're at the end.
Okay, so if we're at the end, like if I visited everything and I've come to the very end, that would be okay. But that would be, right. Okay, yeah. So, I think where to go with this. Okay, well, let me go back to these examples, right? So let's think about this. Think about this graph here. So every vertex in this graph has degree 3, right? So that means, you know, no matter what, so wherever I start, I'm going to leave from that vertex and use up only one edge. Right? Wherever I start, I'm going to use up one edge. But then every other vertex I go through, I'm going to use up 2 edges, leaving only one remaining. And that means, like, you know, if I go through all of them once, every single vertex is going to have one edge sticking out of it. And I can't possibly, like, I can't end at all of them. Right? As soon as I go to another one, as soon as I go to any vertex a second time, I'm stuck there, and I have not visited the other ones. So that actually is a proof for this one that it's not possible to find an Euler path, because, you know, let's just try it. If I start here, if I go along here, I'm not stuck. I can leave here, right? But now this edge here is the only edge left. I'm not stuck here, so let's go this way. You know, maybe let's go this way. I'm still not stuck. And then, but now I'm stuck. Right? I reached this one for the second time, and I'm now stuck there. Right? But these 2 vertices, so like this vertex and this vertex, I only visited them once, and I can't visit them a second time because I'm stuck now. And I couldn't possibly visit both of them because I'd get stuck at either one, if I was even able to get there. Okay. So let me draw another example graph. Let's talk about this one. Is there an Euler path in this graph? Many people say yes, they think there is. Some people say no, there's not. I don't think you end up
start from the bottom of it, and then,
Where, here, or?
I guess,
Middle one?
the southwest vertices,
So,
or that,
yeah.
and then, I just trace the entirety of it from there.
Okay.
Yeah, actually the other way.
Other way. Go back to there.
Yeah, and then that leads into,
Right.
that is,
Yep, that works. Great. So let's think a little bit more about, so this one does have an Euler path. So what are the degrees of the vertices? So these vertices here all have degree 2. Right, so all of those, if I go through them, I will go through them, and I won't get stuck there, and I'll keep going, and then I will have used up all the edges. I never need to come back to that vertex, right? But these vertices here both have degree 3, right? So these ones I kind of have to be careful with. So why is it that, right up here it seemed like odd degree vertices were a problem, right? Why is it okay here? Why am I able to find a path here? Yeah.
Because there are only 2 of them.
Okay, and why does the fact there are only 2 make a difference?
Because as far as like, the thing you drew right above this, you drew in terms of like, it's in the middle of the graph. But if you start a graph from an odd one, there's essentially an even one afterwards.
Right.
And so you pass through again fine. So if you have 2 that are problems, you know that if you start at 1 or end at 1, it'll be fine. And then it'll be fine.
Exactly. That's exactly right. So if there are 2 of these, then I can do it because, well, but I know I'm going to have to start at one of them. Right? If I start like down here, I can guarantee that I'm screwed because, like, when I go through this vertex here, I'm going to leave a straight edge that I can't get to without getting stuck. And if I ever come back to the vertex where I started, I'm immediately done. Right? And so that's not going to work. But it does work if I start from one of these ones with degree 3, and I have to finish at the other one. Because I'm going to go through it once, and then I'm going to come back and finish there. That would give me an odd. So there's lots of ways to do it, but it's essentially going to. Or we could even, we could go this way. Whoops. We could go this way, and keep going this way, and come around like that. Like a lot of ways it works, but they all of them will start at one and end at the other. That also implies that this graph does not have an Euler circuit. If we have to start at one and end at the other, then of course we can't have a circuit because we can never end at the same place as we started. Okay. So next time we will actually see if we can state a general theorem that says when it's possible to do this and when it's not. See how we would